With snowball Earth and the great oxygenation events of the Precambrian, it's only natural that we wonder, was early Earth more extreme than it is now? And if so, why? So in the Precambrian Eon, from the beginning of Earth's accretion at 4.6 billion years ago to around 540 million years ago, there were more extreme climatic and environmental changes that occurred compared to the current eon, the Phanerozoic Eon, which has gone from the end of the Precambrian, 541 million years ago, to the present day. These major events in the Precambrian include oxygenation events like the GEO, the Great Oxidation Event, and the NOE, the Neoproterozoic Oxygenation Event, which rose oxygen significantly on Earth. The reason for this is because there was first the evolution of photosynthesis, and then you had a lot of factors come together during the Neoproterozoic, like the breakup of Rodinia, and more photosynthesizing organisms evolve, and all of these things to cause another oxygenation event. And this eon also saw two major ice age events that we call snowball Earth events around 2.3 billion years ago and around 600 million years ago. The reason we call them snowball Earth events is because nearly the full globe was covered in ice, which has not happened since the Precambrian. The NOE and the GOE, the oxygen rising events, directly correlate with the timing of the snowball Earth events. Why? Well, oxygen increases due to photosynthesis, decrease carbon dioxide because photosynthesizing organisms take up carbon dioxide and produce oxygen, and this drives cooling because a decrease in atmospheric carbon dioxide causes cooling. And once cooling starts, it can intensify due to what are called positive feedbacks. Positive feedback mechanisms are patterns in which one climatic trend causes the exacerbation of that climatic trend. In other words, cooling leads to glaciation, which leads to more cooling because more ice on the surface of Earth reflects more sunlight and therefore cools Earth even more. There are also negative feedback mechanisms that balance out the current trend. However, this positive ice feedback is one of the major reasons that the snowball Earth events got so bad. But why did these ice age events become complete snowballs? Why didn't glaciation stop toward the equator? Because in the Phanerozoic Eon, since around 500 million years ago, ice ages haven't ever covered the whole planet again. So, why have they been less severe in more recent Earth history, and why were they so severe on early Earth? On one hand, these events were more drastic than Phanerozoic ones because oxygen was still drastically increasing. So we know that oxygen wasn't really at all even present on early Earth from around 4.6 to 2.5 billion years ago. However, it started to jump at that point because of the evolution of photosynthesizing organisms that produced oxygen by splitting water using CO2 and light energy. This caused the Great Oxidation Event, which coincided with the first major snowball Earth event, or what's called the Huronian Ice Age. Then we had a period of kind of low but present oxygen levels throughout the Proterozoic, or from around 2 billion years ago to around 600 million years ago, which is when we had the NOE, the Neoproterozoic Oxygenation Event, that rose oxygen again. And this time it rose it all the way to near modern levels, and then it kind of stayed steady from then, around 550 million years ago at the beginning of the Precambrian, till today. And so this steadiness and relatively high concentration of oxygen in the Phanerozoic compared to the Precambrian may have contributed to the more drastic conditions in the Precambrian and less drastic ones in the Phanerozoic. However, there are other factors that seem to have contributed to the more intense events of the Precambrian, including different atmospheric concentration. Well, this kind of goes back to the presence of oxygen, but we'll talk about other atmospheric gases that might have played a role. There was also a difference in solar radiation. There was a lack of complex life. Again, most of the life in the Precambrian was microbial and single-celled. Multicellular life did evolve in the Precambrian, but large multicellular organisms like animals didn't evolve until the Neoproterozoic and Cambrian time, right kind of during and after the second snowball Earth event and the Neoproterozoic oxygenation event. And the last factor we'll talk about is tectonics, continental configuration, and ocean circulation. This seems more like three factors, but really the movement of tectonic plates and the configuration of continents kind of go hand in hand, and these can control climatic and environmental events by controlling ocean circulation, ocean and atmospheric circulation. So we'll talk about all of these, and we'll start with the difference in atmospheric composition of the Precambrian. On early Earth, there were much higher concentrations of greenhouse gases like carbon dioxide and methane. This led to an overall warmer climate. However, when photosynthesizing organisms evolved to take up carbon dioxide and produce oxygen, oxygen-respiring organisms weren't yet around to balance out this process. Therefore, when the GEO occurred, the Great Oxidation Event and the first snowball Earth event, there wasn't any animal life to then breathe in that oxygen that the photosynthesizing organisms were producing. On Earth today, they are present and they do balance out that process, but they weren't present here. And so during both of these events, the spike was enormous because there was no balancing act. It was just a full-fledged runaway oxygen increase. Since around 500 million years ago, though, within the Phanerozoic Eon, there has been a much greater balance between the carbon and oxygen cycles, and this has led to relative stability in climate and has potentially contributed to the less intense events of the Phanerozoic Eon compared to early Earth. Next, we have the difference in solar radiation. Solar radiation was less intense in the Precambrian than on modern Earth. Ever since the formation of our solar system, the sun's intensity, or the sun's output, has been increasing, and therefore on early Earth, there was probably a stronger albedo feedback. Remember the feedback I mentioned earlier, when ice spreads at Earth's surface, there's a stronger reflectivity of solar radiation and therefore further cooling, and this exacerbates the cooling trend. This reflectivity of Earth's surface is called albedo, and so this feedback in which cooling led to more ice, which led to more cooling, would have greatly contributed to the snowball Earth events, especially considering that the sun's output at the time was much less than it is today. However, I think one of the major reasons things were more intense on early Earth is the lack of complex life on early Earth. For one, there was a lack of land plants and soils. Today, land plants and soils regulate global climate by sequestering and storing carbon. I talk a lot more about this in my carbon sequestration video, and what's important that I point out in this video is not only the sequestration of carbon dioxide by plants that are photosynthesizing, but the storage, the long-term storage of carbon in the soils. And this can really help to regulate climate change events and climate trends and help them from not becoming so extreme or becoming runaway effects. But it's not just plants and soils. There was also a lack of complex animal life and complex ecosystems on early Earth. Animals respire O2, like I talked about earlier, and release carbon dioxide, thus balancing out the process of photosynthesis, which that balancing act wasn't available during the Great Oxidation and Neoproterozoic oxygenation events. Moreover, ecosystems of complex plants, animals, fungi, and microbes on modern Earth, on Phanerozoic Earth, maintain the major biogeochemical cycles. These are the cycles of, the elements that are necessary for life: carbon, hydrogen, oxygen, phosphorus, nitrogen, and sulfur, etc. And these balance Earth's climate and environment to keep everything going. And billions of years of evolution has diversified these ecosystems, and this diversification makes climatic and extinction events less severe, because the more diverse ecosystems are, the more likely certain things will survive extinction events and major climatic and environmental changes. Additionally, competition, as well as diversification, has prevented the overdominance of any one species. On early Earth, the exact opposite happened: a lack of diversity and the overdominance of a few major species, especially things like cyanobacterial bats, likely contributed to the intensity of the events at the time. However, it wasn't all lack of complex life, lower solar output, or different atmospheric composition. There was also a different configuration of continental land masses, and therefore a different ocean circulation pattern on early Earth that affected the global distribution of heat and moisture. This may have caused more frequent and severe weather events like hurricanes, cyclones, and monsoons, but it also, on a global scale and a long-term geologic timescale, might have prolonged ocean stagnation and anoxia. Ocean stagnation just kind of means a stagnant ocean or a poorly mixed ocean, especially from deep to surface waters, and this can cause deep ocean anoxia to become globally widespread. And ocean anoxia is the lack of oxygen in the water. And oxygen is necessary for oxygen respiring life like animals. And so this prolonged ocean anoxia within the Precambrian time might have prevented animals from evolving until the Neoproterozoic oxygenation event rose oxygen concentrations to the point that it ended this ocean anoxic trend and began to fully oxygenate the ocean so that animals and other oxygen respiring organisms could evolve. But changes in continental configuration and associated ocean anoxic events have continued to occur through the Phanerozoic Eon too, so since 500-ish million years ago. And so this is not something necessarily unique to the Precambrian. The reason ocean anoxia was more severe and more prolonged in the Precambrian again goes back to the lower overall concentrations of oxygen. It's easier for anoxia to spread, a lack of oxygen, if there's already a lower overall amount of oxygen available. And so this is likely what caused the difference in the intensity of ocean anoxia in the Precambrian compared to the Phanerozoic. It wasn't necessarily the different continental configuration or ocean circulation, because those aren't unique to the Precambrian. That has occurred, and those things have changed throughout the Phanerozoic as well. However, something that was fundamentally different in the Precambrian compared to today is the style of tectonics. Ancient tectonic events are not that difficult to recognize in the rock record, and sometimes they might even still have mountains that are built that we can easily see with our eyes and then reconstruct what happened to build those mountains. However, tectonic styles on ancient Earth are a little more difficult to reconstruct. But even with that said, there have been people that have attempted to do so, and some have suggested that there have been 5 distinct major tectonic styles that have kind of shifted through Earth's history. These styles would include the Hadean tectonic style from around 4.6 to 4 billion years ago in the Hadean Eon of the Precambrian, then the early Archean from around 4 to 3 billion years ago, the late Archean from around 3 to 2.5 billion years ago, the Proterozoic from 2.5 billion to around 800 million years ago, and the Neoproterozoic to the Phanerozoic, or today. So from around 800 million years ago to the present. And so this 5th one here represents modern style plate tectonics. However, plate tectonics per se has not always been the way that tectonics has occurred on Earth. On early Earth, there was something called drip tectonics that was plate formation, and there were some other styles that I'll talk about on the next slide. But what I want to initially point out with this slide is the timing here of these transitions. Note the timing of the 2.5 billion year transition and the 800 million year transition coincide directly with the snowball and oxygenation events of the Precambrian. So this clearly indicates that, maybe it's not showing direct causation of tectonic style to these extreme events, but it is showing correlation, and that's something to at least look further into. Before around 2.5 billion years ago, there was likely stagnant, what's called lid tectonics, with small-scale block jostling. So from what I read about this, it sounded like kind of like protoplate type things were jostling around, but there was no necessarily like subduction yet of rigid plates. There was rifting that was occurring at a small scale, and compression and strike slip faulting. So rifting is the extension of crust and then the extrusion of new mantle material that cools as new crust. Compression is the pushing together of what today would be plates, but on early Earth was just one big kind of lid that was kind of pushing together in some parts, and this might have caused some folding or these kind of dripping features of plate tectonics. There was also strike-slip faulting, so this is kind of the what we call today like transition plate boundaries that are sliding against each other but not pushing or pulling. And so all of these things were happening on small scale, but it was all kind of more, from my understanding, droopy rather than rigid and like, plates. I don't know if that makes sense. I have a person in my audience that knows so much more about Precambrian tectonics than me, Steve Bauman. So if you're out there and you're watching this, please comment to better explain the tectonic style of the Precambrian. In any case, global subduction didn't occur until after 2.5 billion years ago. And the Boring Billion, from around 1.8 billion years ago to around 800 million years ago, saw the first two supercontinents form. Columbia around 1.8 billion years ago and Rodinia around 1 billion years ago. And the breakup of Rodinia seems to have began modern style plate tectonics. So this was the first time that plates had fully distinguished themselves and started to subduct under one another and all of that. Now, given the timing correlation as well as the close relationship between tectonics and global heat flow, it likely greatly affects and has greatly affected global climate throughout Earth's history. However, the exact role that tectonic style has played in causing early Earth's more extreme events is still uncertain. So I encourage you to go into this research if you're interested. Maybe reach out to Steve. He seems to know a lot of stuff about this. So now I've talked about all of the reasons that I found for why early Earth seemed to be more extreme. But does that necessarily explain why modern Earth has been relatively less extreme? Well, the relative stability of Phanerozoic climate, so everything post 500-ish million years ago, is often attributed to the presence of complex life, like plants and animals. I talked about earlier how the lack of complex life on early Earth might have contributed to extreme events because complex life on modern Earth regulates climate, especially processes like photosynthesis, carbon sequestration and storage, and respiration. Really, it's been kind of all about the balance of the carbon cycle throughout the Phanerozoic that has caused major climate change and extinction events when this balance becomes tipped due to volcanism or impacts that release a bunch of carbon to the atmosphere, or, the evolution of non-vascular and vascular plants, which take up a bunch of carbon from the atmosphere and tip the balance the other direction. And so whenever this balance tips, it has had major extreme events on Phanerozoic Earth, but in general, there's been a good balance between atmospheric and buried carbon, and this has regulated climate throughout the Phanerozoic. But this is not to say that there haven't been several significant ice ages and warming events in the Phanerozoic. There have been, and these events have been caused by a multitude of factors, which I talk about in a whole separate 2 videos about extinction causes. I have the top 3 mass extinction causes and also extinction causes nobody talks about video. I'll link the top 3 up to the top right for you so you can check it out if you're interested. Lastly, I have to mention this because I think that, it's important that we realize the intensity of early Earth events like snowball Earth and stuff. But it's also important that we kind of orient ourselves within geologic time. It's clear that changes on early Earth were a bit more drastic than post-Cambrian Earth changes. However, it's not actually been that long, geologically, since the last drastic event. The 2 major snowball Earth and oxidation events were separated by about 1 billion years. And since the last major Neoproterozoic oxygenation event and corresponding snowball Earth event, it's only been about 600 million years. So only about half that, meaning that there could definitely be more extreme events in Earth's future, potentially even more extreme than these early Earth events, especially given human activity right now. So I just want to show on the time scale that's actually to scale. So many geologic timescales, if you search geologic timescale, they expand the Phanerozoic time to make it more detailed, but it's not to scale. When you put it to scale, the Precambrian is this huge time where in between these major events, there wasn't really that many extreme events. We call it a boring billion for a reason. And so it's important to remember that it's only been a relatively short time since the last extreme snowball Earth event. And yeah, it's possible we could have another very extreme warming or cooling event in the near or far future in Earth that could still continue this trend of, every billion years having a big event. So it's hard to answer the question of whether early Earth was more extreme because of this time consideration. However, it is clear that, things were still finding equilibrium back then because oxygen wasn't around and then it was around, and that was a big change. And it didn't have any balancing things like oxygen respiration wasn't a process yet. So obviously things were more extreme, but it's still hard to say because things could go extreme again in the future and continue this trend. So anyway, I find it really interesting, this topic, and I want to thank the person who asked this in the comments, asked why things on early Earth seemed to be more extreme. I tried to go back and find the comment and I couldn't, unfortunately, but thank you, whoever you are. Comment down below if that was you. But yeah, I thought that was a really interesting video idea, so I hope you guys enjoyed it as much as I enjoyed making it and learning about this. And as always, my references are linked in the description box below. And if you want to check out other videos about extinction events or extinction causes, I will link a couple on either side of my head here, and you can check those out. See you guys next time. Bye.